Aloha! In this video, we will discuss potential pitfalls of data management. These issues are prevalent. Nonetheless, there are solutions and proactive actions that can be implemented easily and quickly. By prioritizing well-organized, thoughtful data collection and management, you can avoid unnecessary headaches and ensure your results are accurate and easy to interpret. Have you ever tried to conduct data analysis only to discover that the data are poorly formatted or riddled with errors? Often, this leads to spending 90% of your time on data cleaning and formatting, a frustrating and avoidable experience. No sophisticated statistical procedure can salvage a project burdened with messy, faulty data. Proper research design and thoughtful planning of data collection can significantly streamline later stages of analysis. Unfortunately, outdated data management practices often add unnecessary work, confusion, and even errors. Consider this example. Can you find something problematic? First, there are too many options, which would cause confusion. In addition, assigning placeholder values like 99 to represent missing, NA, don't know, or don't remember can be problematic. If such non-data are left in the dataset and forgotten, the results will be skewed. Why not leave these fields blank instead? Please pause and reflect. What is the problem in these options? First, -5, -4, -3, and so on are redundant. You will remove them from data analysis anyway. Second, when numbers are assigned to rating scales, it is more intuitive to assign larger values, for example 5, to positive responses such as very important or very good, and smaller values, for example 1, to negative responses like not at all important or poor. Please pause and reflect on this problematic practice in data management. These surveys were designed by professionals, but using such a counterintuitive method increases the risk of misinterpretation. These counterexamples are found in World Value Survey. Again, very important is coded as 1. Although you can reverse the scale later, starting with the correct scale can minimize rework during analysis. Inconsistent coding schemes across survey questions further complicate analysis. Take, for instance, the Program for International Student Assessment, PISA, where 1 might mean strongly disagree in one question, but strongly agree in another. This inconsistency forces analysts to mentally reverse scales, increasing the likelihood of errors or contradictory conclusions. While it's possible to adjust scales during analysis, why not standardize them correctly from the outset? In some surveys, rating scales are not evenly spaced. For example, the online ADHD test uses a scale of 0, 1, 3, 4, and 5, omitting 2. Such irregularities can complicate analysis and interpretation. Mismanagement of data can lead to disastrous outcomes. A notable example occurred in 2013 when a large-scale survey mistakenly labeled Hong Kong as the most racist city in the world. The error stemmed from a coding mix-up. Willing was coded as 1, while unwilling was coded as 2. In the analysis, the codes were inadvertently swapped, reversing the results. In reality, the majority of respondents were willing to have neighbors of a different race. To avoid such errors, it's far more intuitive to code yes as 1 and no as 0. Using 1 and 2 for binary responses introduces unnecessary ambiguity. Even basic codes like gender can cause significant errors when they are mistakenly swapped. Many people coded categorical data into numbers, but is it necessary? Pause and think. How can this extra step benefit your data management and analysis? Nothing. In contrast, it increases your workload. You need to go back and forth between the data table and the codebook. Whenever you have an extra layer, you increase the risk of making mistakes. The best approach? Minimize coding, or eliminate it altogether when possible, such as using M for male and F for female, W for white and B for black, 1 for yes and 0 for no, can enhance clarity. This intuitive approach reduces the need to constantly reference a codebook and minimize the risk of errors, especially when data are passed between people or revisited after a long period. There are situations where coding is necessary, such as country or program classifications. Countries often have multiple names. For example, the United States, United States of America or America, Great Britain, United Kingdom or England, South Korea, or Republic of Korea. Standardized codes like US or USA, GB or GBR, and KR or KOR ensure clarity and allow for seamless data merging. Classification codes, for example CIP, can standardize academic labels and streamline education datasets effectively. Some coding schemes are outdated, rooted in a time when computer storage was expensive. For example, years were trimmed from 4 digits to 2, and year-semester combinations were reduced from 5 digits to 4. Today, storage is cheap, and such practices are unnecessary. Consider this example. You encounter a column labeled semester or term with the value 2017. At first glance, you might assume it refers to the year 2017, but it actually represents fall 2001. Here's how it works. The first 3 digits indicate the year, with the second digit trimmed, and the last digit represents the semester, 1 for spring, 5 for summer, and 7 for fall. This outdated scheme is unnecessarily confusing. There are instances where numeric coding might still seem practical. For example, in SPSS, categorical variables represented as letters sometimes disappear from dialog boxes when running certain procedures. SPSS restricts string variables in some contexts. Transitioning such cases to numeric codes offers workarounds. However, reinterpreting strings as numbers can confuse users and compromise analysis integrity if done carelessly. To rectify the situation, it is advisable to choose statistical software tools like SAS or JMP, which work seamlessly with both text and numeric variables. Coding categorical data as numbers introduces another problem. Please pause and reflect. What's wrong in the following table? Did you see something funny? The mean of gender is 1.38. How could it be? Inexperienced researchers may mistakenly analyze the coded variables as continuous. I've repeatedly seen reports of average gender, average religious affiliation, or average employment. Categorical variables such as race can be used in regression analysis if the data are dummy-coded. But some people treated the codes as continuous and reported the coefficient of ethnicity. These nonsensical results arise from misinterpreted coding. To avoid such pitfalls, I recommend using descriptive labels rather than numeric codes whenever possible. This approach prevents confusion, speeds up analysis, and produces outputs ready to be pasted into reports without needing to consult a codebook or manually adjust labels. There are scenarios where shorter labels or numeric codes are necessary. For running models like confirmatory factor analysis and structural equation modeling in SPSS, JMP, or SAS, employ shorter labels can prevent interface errors and maintain readability of outputs. It is advisable to use numbering variables for bulk data programming, easing scripting and future adjustments. If you have a lot of variables, this approach can save your time from typing. Numeric naming also facilitates array manipulation. For example, if you name your variables as Q1 to Q100, you can easily alter them in an array because the numbers are consecutive. Mismanaged data can make analysis confusing, inefficient, and prone to errors. These tips are intended to help you recognize potential pitfalls and adopt better practices. Keep in mind, just because a convention has been widely used for years doesn't mean it isn't an uncorrected mistake. Thoughtful, modern approaches to coding and labeling can save you time and prevent unnecessary headaches. Thank you for watching this video. I hope these tips can improve your efficiency in data management and accuracy in data analysis.